sign said, build a nuclear power plant at this price and the price is fixed. And so at this point, the price has gone so far over what they initially estimated that there are no good consequences that can come from this. This is being challenged though in legal battles and has been in legal battles for a long time. But if Finland ends up having to foot the bill for that, it will without doubt bankrupt the utility in Finland, which would then revert back to the government of Finland, which will probably bankrupt the government of Finland. And if Ariva ends up footing this bill, it will bankrupt Ariva, which will have probably not bankrupt France, but it will have a huge negative impact on France. These are the things that make it so hard to get people to invest in stories like this, and there are lots of those that make it so hard to get people to invest in nuclear power. So, given this, who produces the most nuclear power in the world? Well, the U.S. So this is the fraction. Sorry, this is the fraction of power produced from nuclear, and so in terms of a fraction of your electrical power, France produces the largest percentage of their power from nuclear power, and that's almost 80% of their power comes from nuclear energy, so that's a lot. And you can see how the rest of the countries come down here. There were a couple of countries where this was 100% for a while, but they closed those reactors, and these countries now have 0%.
Where was Japan like 5 years ago?
Japan was probably about second or third in this list, so it was a fairly significant amount of their power. That's why I circled here. So now it's down to nearly 0% of their power being.
So what's it going for? Down to coal?
Mainly coal. Well, basically everything they could find, but coal was the biggest contributor. And they're still struggling with that. So they don't know. They don't have a stable energy policy in Japan right now. Nobody believes that they can continue what they're doing right now for very long. So they've got to either come to grips with restarting these nuclear reactors, which is very unpopular among the people in Japan, or converting to some other. Now, in terms of actual generation, so this is suppressed. So the U.S. on this scale is at 798, and France is at 490. That's so far out here that everything else would look like zero. So the U.S. generates essentially nearly twice as much energy from nuclear power as France. And France generates about twice as much as Russia, and then everybody else kind of follows, as you can see here. So the U.S. is by far the largest generator of nuclear power in the world. France has the largest percentage of nuclear power contributed to electricity. Russia is the large nuclear power contributor, and then you can see where the rest of the countries fall in line here. Japan, and we circle them. So this is the amount of nuclear generation in Japan. So
I noticed China's building a lot of reactors. How long will it be before they catch up to us?
So China had been building mostly, China's economy has been exploding for a long time. So it's slowed down to 7% roughly GDP growth right now, as compared to, anybody want to know what the U.S. GDP growth is? About 1.5%, all right? So their economy is growing, and they think they're in a crisis right now. Their economy is growing up to 7%. And they probably are kind of in a crisis, frankly. But depending on what they do with it, so up until last year, China's power plan was to pretty much fossil, mostly coal-based power production. They were building, there was a time when they were commissioning a coal-fired power generation station every week, once a week. So, which is an astounding rate of growth. But they are, if they're going to meet the commitments that they made for CO2 reduction, that's going to have to stop. And nuclear is probably about the only option. Nobody knows. China is doing some really innovative things with nuclear power. They have some new nuclear power designs that they're willing to permit that we don't permit in the United States, or it take us so long to permit them that nobody wants to start. So in terms of government-sponsored, land-based power generation facilities, China is doing most of the innovation right now. but nuclear power still makes up, I think it's only 17%, if I remember the number right, of their total power generation. Nuclear is starting to increase rapidly, and coal is starting to decrease. And this is the age of the nuclear fleet worldwide, so you can see that most of the nuclear power plants are 30 years old. Most of the coal-fired power plants are more like 50 years old. So they're mostly 1970s technologies, designed in 1970s, built in the late 70s and 80s, and up into the early 90s. And then there's hasn't been zero construction since then, but worldwide a lot less construction of new nuclear power plants since Chernobyl was really what caused this, and Fukushima probably might have a similar effect. All right, so let's talk about how they work. So first, some terminology. So fission, I think obvious to everyone, fission is the dissociation of a nucleus into two unequally sized major fragments and a number of neutrons and some alpha particles typically. A fissile fuel is a fuel that fissions upon absorption of a neutron. And all fission reactors have to have either fissile fuel or fertile fuel. Nuclear power always comes from fissile fuel. Examples of that are uranium-235 or plutonium-239, the two most important examples. But there are some reactors, well actually all reactors, that produce some fissile fuel from fertile fuel. So you put fertile fuel in them, and a fertile fuel is something that becomes fissile when it absorbs a neutron. So it doesn't actually, there's no fission event, but you absorb a neutron and you convert U-238 to plutonium-239, and plutonium-239 then undergoes a fission event. So there are no reactors in commercial operation right now, but thorium-232 is probably the next most important fertile fuel that people are thinking about using for nuclear power. So when you generate when these things come apart, we talked about how energetic it is when the nucleus comes apart. The fragments of the nucleus move at extremely high velocities, and the neutrons themselves move at very high velocities. They measure these velocities traditionally in electron volts, and a typical neutron upon a fission will be what we call a fast neutron. It means it has a lot of energy. Energy is on the order of 1 to 3 mega electron volts. In extreme cases, they get up to 7 or 8 electron volts. But those are rare neutrons. And like many things in nuclear energy, everything is kind of backwards in nuclear energy from what you usually understand. So in normal chemical kinetics, it's the rapidly moving molecules that react. It turns out in nuclear power, it's the slow-moving neutrons that are most responsible for the reactions. In fact, the rapidly moving neutrons don't cause much to happen. So in a fission reactor, in a slow or thermal reactor, as they call them, which is most of the reactors we built, almost all of them, what you have to do is slow those fast neutrons down so that they get down to little under 1 electron volt. So you're going from several mega electron volts down to less than 1 electron volt. So typically, typically it's 0.025 electron volts is the target you try to get them to. They call those thermal electrons or thermal neutrons or slow neutrons. And that's the level of energy they would have if they were just bouncing around in equilibrium, bouncing off nuclei in the reactor, and that's where you try to get them to. So the design of most reactors is to take the very fast neutrons that are initially generated and to slow them down and turn them into slow neutrons. And the thing that does that in the reactor is called a moderator. And in most reactors, water is used as the moderator. So when you hear people say this is a water-moderated, water-cooled reactor, water is both cooling the core, but it's also slowing down the neutrons. And the things that you want to use for moderators tend to be very light things, but most importantly, they need to be things that do not absorb neutrons very effectively. So you want things where neutrons will just bounce off the nuclei, exchange energy in that collision, but not be absorbed in that collision. And that's the difference between heavy water and light water. So normal water, which has mostly hydrogen, normal hydrogen, hydrogen-1, has higher absorption probability than heavy water. And if you use heavy water, the likelihood of losing the neutron to an absorption into the nucleus is much lower, and therefore you don't lose as many neutrons. And so if you use heavy water, you don't need as many neutrons in order to get the reactor to work, and that's why you can use normal, just normal, lower natural uranium to fuel a reactor. But for every other kind of reactor, if you're using water or almost anything else as the moderator, except for carbon-12, then you need to enrich the uranium so that you have more neutrons than you naturally have. So that's the difference between slow and fast neutrons. So fuel rods. So you've all probably heard of fuel and control rods. You might not recognize that they're about the diameter of your little finger, and they're 12 to 14 feet tall. So they are tiny, tiny. There's just skinny rods that you put into these nuclear reactors, and there are thousands of them in a nuclear reactor. Why would they be so skinny? Because you need a large surface area because they get so hot in the inside that if you made them any bigger, they would melt in the core, and then you would have a molten reactor, which is really bad from a safety standpoint. That's like the worst thing you could do. So you make them very thin, and one of your homework problems is going to be calculate the temperature profile on a typical fuel rod, and you'll see that they're typically about 1 centimeter, about half an inch in diameter, and in that 1 centimeter you go from several thousand degrees to just a few hundred degrees in a really steep temperature profile. So that's so the fuel rods are really skinny. The control rods are similarly skinny. They don't have to be skinny for the same reason. They just are usually skinny because they go into the same kinds of holes that the fuel rods go into. They are actually sometimes a little bigger. When you generate these neutrons, you generate what they call prompt neutrons, and this is more than 99% of the neutrons are generated almost instantly. It turns out two different agencies of the government that have both of whom have significant amount of effort or significant amount of influence in the nuclear industry have different definitions for what a prompt neutron is, but they are functionally about the same. They're essentially instantaneously generated neutrons. So neutrons that are generated in less than 10 to the negative 13 seconds or less than 10 to the negative 14 seconds after the fission event are called prompt neutrons. And so you think about this for a minute. If I have this prompt neutron, I'm generating neutrons, and I've got this set up so I have a chain reaction, so I'm generating just as many neutrons as I need to keep this going at a steady state. What happens if I have just slightly too much, if I generate just slightly too many neutrons, and they're being generated at a rate of 10 to the, they're being generated every 10 to the negative 13th or 10 to the negative 14th seconds. So that means that if I have slightly too many, that chain reaction, even if the reactivity, the ratio is like 1.000001, in 1 second you go through 13 generations of accumulating neutrons. So in less than a second, the reactivity of this reactor will just blow up. Way faster than anybody could respond to try to turn the reactivity down. Or the other way, so that's catastrophic. The other way is not catastrophic, but it's still just as difficult on the reactor. If you don't have quite enough reactivity, then the reactor just shuts itself down. And both of those things would happen effectively instantly in terms of the time that human beings can react to them. Fortunately, there are delayed neutrons. And these represent less than 1%, typically 0.6 to 0.7% of all the neutrons. And they aren't generated quite as quickly as these others. It takes seconds to minutes for these neutrons to be generated. Actually, the neutron generation is virtually instantaneous, but it occurs during beta emissions mainly. There are a few of the fission products that decay, and during their decay they generate more neutrons, but it takes a few seconds to maybe a minute for them to decay. And 100% of the control of a nuclear reactor relies on these delayed neutrons, which represent less than 1% of the total neutrons that are being generated. So the way a nuclear reactor works is you get it up so that the prompt neutrons, based on prompt neutrons alone, you're always subcritical, meaning you're not quite generating as many neutrons as you need in order to keep the reaction sustained. And then you control the reactor, and these seconds to minutes that you have with these delayed neutrons is what gives you the time so that you more or less are oscillating in the reactor between slightly too many and slightly too little, which should never be exactly right. So the reactor is controlled, and it's these delayed neutrons that give you the ability to keep the reactor from either running away instantly or shutting down instantly based upon these very rapid neutrons. And then there are these void coefficients, or void and temperature coefficients, and these are also important considerations. So if the reactor starts to run away, the first thing that it does is it starts to heat up. And when it heats up, things expand, even if it's, so let's just talk about just the temperature. So as the temperature increases, the metal expands a little bit in the fuel rods, and the water expands, and the concentration of the moderator decreases because the density is now a little lower. The concentration of the fuel decreases because the density is a little lower. And reactors that are designed in a way that as the temperature increases, the reactivity automatically decreases are said to have a negative temperature coefficient. Or as the temperature increases, all of these reactors, we'll go through this in just a minute, but most of the reactors, with the exception of the boiling water reactor, they're designed so that they don't boil the water. They just heat it up to a very high temperature, but it doesn't boil. But if the temperature starts to get too high, then you start to form bubbles, or voids is the way they talk about it. And depending upon the design of the reactor, if you form a bubble, the reactivity can either decrease or increase. That is, the propensity for forming neutrons will either decrease or increase. If it decreases, then you have a negative void coefficient. That means if I start to boil water, the reactor will automatically, without any intervention from anybody else, just because of the physics of the situation, it will start, the number of neutrons will automatically start to decrease. That will decrease the temperature, and the boiling will go away. In the western United States, you cannot get a permit for a reactor that has a positive temperature or void coefficient in the western world is what I meant. So but the RBMK reactors, in part of their operating regime, actually have a positive void coefficient, and that actually figured prominently into the Chernobyl accident. So we'll talk about that when we talk about the accidents. So one more thing to talk about is the cross section. So if this is a uranium-235 nucleus, then we talk about cross sections, and there are cross sections for absorption, and for fission, and for collisions, and for everything else. But the cross section says, from the standpoint of a neutron being absorbed, how big does this look like it is? So that is, this is the actual physical geometrical cross section. Cross section is a measure of area, and the technical term for it is barns, right? So it's like the side of a barn. So most nuclei are 1 to 2 barns big in terms of their cross section, in terms of their physical cross section. But if you can get an incident thermal neutron that is a slow neutron anywhere near this nucleus, you don't actually have to collide with the nucleus in a physical sense. So even if, the fission cross section is about 582 barns. So that's a long ways away. If this neutron passes within the 583 barn target region around the nucleus, it causes the nucleus to fission. So that's a little mind-boggling when you think about it. So this neutron goes through here. That's a long ways away from that nucleus, and when the neutron goes by, that nucleus fissions. So that's part of the quantum mechanics of what's going on in this situation. Even though this has a physical size, it's about like this. It has an influence in terms of its wave behavior. It's much larger than that, and it's so unstable that you don't have to get that close to it. If you think of this as a wave, and the wave is decaying as you get from that center part, and the nucleus interacts with that wave clear out here, and that's enough of an interaction to cause this nucleus to fission, even though geometrically speaking, they're still quite a large distance away from each other. So this is the way cross sections vary with the energy of the nucleus. And notice this is a logarithmic scale that covers 15 orders of magnitude. So This is a huge range of variation. So we start off at low energies. We start off, and these are very low energies here. We start off with cross sections, fission cross sections for uranium-235, and so the red line is uranium-235, plutonium-239 is the purple line, and the green line is uranium-233. So those are all fissile materials, and so their cross sections at the very low neutron energies are over 10,000 barns. So remember the physical diameter is 1 to 2 barns. So you don't have to get very close to this nucleus in order to get it to fission. But as the energy of the neutron increases, this decreases, and this may not look like much of a decrease, but these are orders of magnitude decrease. And so by the time we get up to the mega electron voltage of prompt neutrons is clear out here. So we are many, many orders of magnitude smaller in terms of the cross-section when these neutrons are moving rapidly than we are when they're slow. So the design of slow reactors or thermal reactors is the neutrons are always going to be generated with energies that are out of here, and we need some way to slow them down, and as we slow them down, their likelihood of causing fission increases dramatically, and it's the slow neutrons that are actually driving the reaction in the system. So in reality, those neutrons spend most of their lives as slow neutrons. This is a logarithmic plot, and this is a logarithmic plot. And if you were to plot this on linear scales, this line would look like it would just come down like this and come out like this. So over the great majority of the lifetime of the neutron, it's actually in its very slow, it's moving slow. So we moderate, most reactors are over moderated. So we have two kinds of reactors: thermal reactors, which is all but 2 of the 434 reactors that we build are thermal reactors that operate on thermal neutrons, just the way I talked to you about. Fast reactors actually use those fast neutrons. They don't have any moderation. And so the cross-section of the fast neutrons is not 0. And so they will actually fission. They actually fission the fissile material at high speeds. But that means you have to have more enriched material because the likelihood of the effective size of those nuclei has shrunk way down, and the chances of it banging into something else where it gets absorbed is increased fairly significantly. So you lose a lot of neutrons to absorption into other things instead of causing the fissile. So we usually try to get them down to well under 1 electron volt. They start off at mostly 1 to 3, sometimes up to 6 mega electron volts. So fast reactors can be either breeder reactors or not breeder reactors. So a fast reactor just means that you're using the fast neutrons. Almost always, if you build a fast reactor, though, you would make it a breeder reactor. So what a breeder reactor means is that it's generating more fissile fuel than it's consuming. So that means that if you fuel a breeder reactor with U-238, for example, you're consuming uranium-238 all the time. Some of that U-238 goes on to in a fission event to produce fission products, but you're actually building up over time the concentration of plutonium-239, which is what you make from. So U-238 converts to plutonium-239, and it's the plutonium-239 that fissions and it creates the energy. But the amount of plutonium-239 is increasing with time. So it's like an automobile that generates more gasoline. Now, you can't, so you're consuming U-238 all the time. So it's not, so people say it makes more fuel than it consumes, and that's true in terms of the fissile fuel, but that's not true in terms of the fertile fuel. So you're burning up U-238, but you're creating more U-239 than you're consuming, and so over time, you can just you have to take the material out periodically, take some of the plutonium out of it, put it back in the reactor, and it builds up more plutonium, and you just keep making more and more fuel. So that means that instead of operating the reactors on the basis of the U-235, 0.7% of the uranium we have, we can now consume the U-238, which is both of them, which is 100% of the uranium. So that makes the amount of fuel that you need to generate a given amount of electricity way, way less. Or alternatively, that means we'd have way more fuel available to us for a much longer time than we would have otherwise. So, with those terminologies, these are some of the parameters for different kinds of fuels. The vast majority of reactors are fueled with U-235, but mostly through weapons decommissioning, we have a bunch of plutonium. Plutonium goes into weapons, and so they mix that weapons plutonium with uranium oxide and make what they call MOX fuels, mixed oxide fuels, uranium and plutonium. But uranium is probably the place to focus here. So you can see the fission cross sections at the energies at 0.025 electron volts. This is about 585 barns. So that's only 1.27 barns at the fast electron speed. So it's almost 500 times more likely to fission at slow speeds than it does at fast speeds. The number of prompt neutrons that you generate is a little over 2. You only need 1 to sustain this reactor, so you can afford to lose 1.4 of them and other things, and in order to keep the 1 to keep driving the fission reaction. At high energies, you actually generate more prompt neutrons, and then the delayed neutrons is a small fraction of that. You can see the delayed neutron fractions there. And these are the ones that are, you might think they're ignorable, but they are critically important to the operation of a safe reactor. And if you look at plutonium, it generates a little bit more reactor. But now compare that to U-238, which is 99% of uranium. So look how much the cross section drops. So you can fission U-238 both at low and at high speeds, but the fission cross sections are much lower. And you generate neutrons when you do that, and you generate actually more delayed neutrons up. So does that kind of give you an idea? If you feel comfortable, you understand the science that's going on in the reactor? Because we're about to talk about the engineering of that. How do you So bottom line is, the reactor generates these very rapid neutrons. You have to slow them down, and then once you slow them down, and there are several ways to slow them down, then they'll react to produce more, and you have to keep the balance exactly right. So on average, even over a relatively short term, the reactivity, the ratio of the number of neutrons you're producing to the number you're consuming has to be exactly 1. And so the only way you can keep it exactly 1 is to be able to bounce up and down around 1 a little bit, and you do that with the delayed neutrons. They're the ones that give you the ability to respond in time so that you can keep the reactivity at 1.
So why exactly is the cross section so small for the slow neutrons and plutonium?
So it's so slow because the scientific reason is that U-235 is turns out that all fissile materials, this is just something interesting to know, have an odd number of nucleons. The U-235 is a huge atom. All right, this could. I'll answer this question, but it's another. I'm afraid of what might happen to your head. Right? So, anybody who wants to wear one of these genuine, probably sweat-soaked BYU football helmets? How many times are you going to have a chance to do that? So just putting that on is a risk to your neck, right? All right. So what holds the nucleus together? That's the real answer to your question. All right. So the thing that holds. So what are protons and neutrons made out of? Quarks, all right? And so they're each made out of 3 quarks. A proton has, quarks come in 6 varieties. Anybody know the names of the quarks?
Up, down.
Up, down, good. Those are by far the most important. All right. Top, bottom, strange, and charm. Quarks, all right? So those are just names of quarks. They don't describe anything, they just give them those names, all right? They're not descriptive at all. So a proton has 2 up quarks and 1 down quark. A neutron has 2 down quarks and 1 up quark. And the quarks are held together with what we call the nuclear strong force. So there's 4 forces in nature that describe everything. The strong force, the weak force. The others are electromagnetic force, and gravity. All right. So those four forces are the only forces we know of in the universe. All right. And of those, all the chemistry that you've learned outside of nuclear chemistry depends upon the electromagnetic force. The chemistry of everything that we do is the chemistry of electrons, not of nuclei. Every chemical reaction you think about is just electrons interchanging. The nuclei don't get involved at all, except in these nuclear reactions. So what holds this? So the strong force is the strongest force we know of. That's why we call it the strong force. And the strong force is what holds the quarks together. And it's a pretty bizarre force. So unlike any other force you can think of, the strong force does not get weaker as you separate things from one another. So if you had two quarks that were separated at a large distance, they would have the same attraction to one another as they would if they were close to one another. So every other force gets weaker as you get further apart. But the strong force doesn't do that. There are a lot of weird things about the strong force. But the strong force is extremely strong, but what holds and it doesn't decrease with distance. But and a lot of people tell you what holds a nucleus together is the strong force. But it's really not the strong force. The strong force holds quarks together. And just like in chemicals, in molecules are held together by electromagnetic forces. But when we make molecules, there are always these local charge distributions. And so what holds molecules together in a liquid, for example, is not the electromagnetic force of the chemical bonds. That is, they're not chemical bonds between molecules. But because of those chemical bonds, there are these weak London forces, or hydrogen bonding that we call them, these weak things that hold the molecules together. And just like that, in the nucleus, the strong force has a residual strong force, and it just kind of leftover parts of the strong force holding things together. And it's the residual strong force that holds the nucleus together. So when we are talking about making energy, we're just talking about the residual strong force, which is a tiny, tiny fraction of the actual strong force. And that's what holds the nucleus together, and that's what's responsible for the binding energies and all the things we're talking about. But the residual strong force, unlike the strong force, decays very rapidly with distance. And so as the nucleus gets bigger and bigger, the nucleons on one side of the nucleus no longer are attracted to the nucleons on the other side. And as the nucleus gets bigger and bigger, the nucleus tends to get less and less stable. And U-235 is the only reasonably stable element that we know of where the nucleus is right on the verge of just falling apart, just through normal. So it's kind of always, just like molecules are always vibrating, the nucleus is always vibrating, it's undulating like this, and it takes almost just a whisper of a perturbation on that nucleus, and it will make it fall apart. So the kind of chemical reactions that we usually undergo don't affect the nucleus at all, so it doesn't even know that they're happening. So they're way long distance away, and the nucleus hardly notices what's happening. So, but when a neutron comes close, that perturbs it. So, but U-238 is much more stable. So even though it's bigger, because there are magic numbers of nuclei, just like there are magic numbers of electrons, and certain configurations of nucleons are more stable than other configurations. So, for example, if you go from helium to lithium in a chemical system, helium is extremely stable, doesn't react with anything. Lithium violently reacts with just about anything that gets close to it. And so, in a similar kind of a way, there are different configurations of nucleons that are more or less stable. And U-238 is quite stable, but U-235 is just about to fall apart. So it takes almost nothing to get the U-235 to fall apart. It takes way more energy to get the U-238 to fit. So all of the elements that are heavier than lead, actually, if you can get them apart, they're actually happier once you separate them. That is, you can fission them. That is what radioactive decay is all about. So they all eventually want to get the smaller things, but they're in kind of a metastable state where it takes a lot of energy to get them over the hump. Once they do get over the hump, they're actually more stable as fragments than they were as their original thing. But U-235, that hump is very shallow, and it takes almost nothing to push it over the hump. So that's why the cross sections are so big. That was maybe a way longer answer than I wanted. All right, so let's talk about how these reactors work. So I have in each one of these cases, I have a cartoon that kind of talks about the essence of the reactor and then a little better diagram. So the pressurized water reactor is by far the most common nuclear reactor. And the way that that works is you have nuclear fuel in here, and you pump water through this nuclear fuel, and the water in this reactor is both a coolant and a moderator, all right? So the water is slowing down the neutrons so that as neutrons come from, and because these neutrons move quite a long distance, so the neutrons are generated in one fuel rod and almost always absorbed in a different fuel rod, so where they cause the fission. So they move from one fuel rod to another. The only time when they can cause a fission within their same fuel rod is if they go through the very unusual event of doing a fast fission as a fast neutron, or if they bounce around in this water and just by chance the collisions turn them back around and they bounce back into the same fuel rod that they came out of. But more commonly they'll bounce into a separate fuel rod. So the water comes up through, keeps the reactor cool, and they never generate steam. And so, but you need steam to run the turbine. So what you do is you pressurize this section of the reactor quite significantly so that you still have water at very high temperatures. And then in the steam generator, they call it, in another heat exchanger, you have water that comes through this heat exchanger, and you have other water that goes through here, and this second stream of water is not at as high a pressure as this one. So if these two can get to the same temperature, or in reality this one's always a little cooler than that, but even at that cooler temperature, this one will be steam. This one's at a hotter temperature, but it's not steam. So a little counterintuitive. So the hottest temperature water is liquid, and the cooler water is steam. All right? The difference is the pressure that they're operating. And so they do this way because for two reasons. One is, so what happens to the heat transfer coefficient on this fuel rod when a bubble forms? So it drops a lot, right? So when you did heat exchangers and heat mass, you know that gases have way lower heat transfer coefficients than liquids do. And so if you have a bunch of bubbles forming here, that means you have the potential for a bunch of hot spots. And like all things in industry, you build them first to be safe, and second to be productive, right? And especially nuclear power plants. The safety concerns associated with that bubble formation are pretty significant. And so rather than deal with those safety issues and form the bubbles, they just pass the water through there as a liquid and keep it as a liquid so that you don't have these localized hot spots that you have to try to deal with. Also, it has a significant advantage that this is going through this environment in here. There's neutrons flying around in there, all kinds of other things happening. It's an extraordinarily radiative environment in here. Lethal to anything, even the smallest impurities, or even without impurities in water, will become radioactive. So this water becomes slightly radioactive just because it passes through the core of this reactor. But if you have radioactive water going through the steam turbine, and you have to do maintenance on steam turbines on a regular basis, that means the steam turbine is now radioactive. So now to do any kind of maintenance, and even during normal operation, the whole thing has to be shielded, and people that work on it have to be in shielded. So it complicates everything else down here. Plus, if you ever have a leak or any accident in any part of this, if this is radioactive water, then that means the leak is going to be, now you're going to have radiation contamination of whatever is being leaked. So for all of those reasons, pressurized water reactors work this way. So this is a little more detailed diagram of what a real pressurized water reactor kind of looks like. So the inside of this containment vessel, they call it this big thick thing here, a containment vessel. So you have in here the nuclear core, and so this is where all the heat's being generated, the part we just looked at. And it turns out the steam generator is, this is the steam generator. The steam generator is usually bigger than the nuclear core. So, but that also goes inside here. So everything that potentially could be radioactive goes inside of here. You're pumping the water through here, and importantly, these are the pumps. This is my next diagram. So you also have, so what happens is, so the temperature of this core changes depending on how much. It doesn't change a lot, but it changes, fairly significantly as you increase or decrease the power of the reactor. But if it's all liquid water, then what's the consequence of changing the temperature of the water? So the density changes, the volume changes, and if you don't have anything for the water to expand into, it's the same as freezing water in a pipe. And it'll rupture seals and pipes and everything else. So there it is. So they also have in here what's called a pressurizer. So, and this is essential to the operation of one of these reactors. And this pressurizer is half full of water, approximately half full of water. And when the temperature increases, then this gives it a place where it can expand into and decrease. And for this to be half full of water, though, what does that mean about the temperature of the pressurizer? So it's at the same pressure as the rest of the primary water, primary loop of the reactor. So it's got to be hotter. And how are you going to make it hotter? Because the hottest part of this reactor is the next core. So you actually have to heat, typically electrically, you have to have electrical heaters inside here. So the hottest part of this loop is actually not in the core, and you start watering it. So the middle of the fuel rods is way hotter than the water. But the hottest water in this loop is not in the core of the reactor, but it's in the pressurizer. Does that make sense to you? And you actually electrically heat that in order to have a little bit of gas phase.
So does it have to be with the saturation temperature then? For the
So it will be at saturation still, but what you're trying to do is generate, well, there's two things that you're trying to do. You generate enough volume of gas so that the liquid can expand and contract without a problem. And then the other thing that they do is they use this for power surges. So because you have this in here, this gas actually can help pump water through. If you need a big boost of power, you can get it out of the pressurizer. So the pressurizer is kind of a mundane thing. It's just a stagnant, mostly stagnant pool of water with some steam above it, but it's critical to the operation of this thing, and somewhat non-intuitively, the water in the pressurizer is actually hotter than the water that comes out of the core of the reactor. So then all the steam turbine and everything is out here. So the steam generator generates the steam that comes to the steam turbine. Then that gets condensed, and this all operates more or less the same way as a coal-fired power plant that we studied, with the exception that the steam that's coming in here is all saturated steam. So remember, it comes out of, it's just being boiled off, comes right off that water, so it's all saturated steam. And so the way they've drawn it here is pretty accurate. So what that means is you go through a few stages of the turbine until you condense typically 6 to 8% of the water, and then you take that water out of the turbine, and you have to continually be extracting the water from the steam in the turbine as you go through the stages of the turbine. So steam turbines are, in principle, in terms of what they do, they're very similar in coal-fired and nuclear reactors, but in detail they're quite different because they're fed with saturated steam in nuclear reactors, not with saturated steam in normal reactors. So some of the features of a pressurized water reactor, the most widely used in the Western and now worldwide, actually, the most common technology that we have. The water never boils in the core. Never there is probably a little bit in quotes. So occasionally you do get bubbles forming in there. They operate right at the edge of boiling, but they're designed to not boil. The heat is exchanged in the second low pressure loop, and it minimizes equipment exposure to ionizing radiation and radioactive waste production. So we'll talk about the boiling water reactor. We should probably take a break. Let's take a break, and then we'll talk about the other kinds of reactors.
What temperature is that water usually at?
So I've got all the specs for both boiling and pressurized water reactors. So we'll go through. So TVA has 3 actually that they're interested in. 2 in this.
There was the 2 in the
Yeah. Right.
2 at some point. We see some.
Yeah, well, there's one more that so it actually isn't the new reactor under construction, it's the one that they did 70 years ago. It started building, and now they're building.
That's good. And that's, so 2 of those. Yeah. For the TVA.
Yeah.
Stanford, Washington, Wisconsin, Michigan.
a positive void coefficient. So these kinds of reactors are cooled with gas. The advantage to that being you're now not limited in the temperature that you'll get here by water, so you can get a higher temperature, which means you can generate a higher temperature over here. And so the gas can be circulated at quite a high temperature and generate a higher temperature steam. But gas isn't going to moderate anything, so they typically use graphite as a moderator. So carbon-12 in particular is an effective moderator. So most carbon includes a little small amounts of other isotopes of carbon. Carbon-12 is the most common. Carbon-12 has a very small neutron absorption coefficient, but the other isotopes have very high neutron absorption coefficients. And so part of what makes this essential, and in fact, in the Nazi efforts to develop nuclear weapons, they failed because they didn't recognize how pure this carbon had to be. They were trying to moderate the reactor with carbon. They didn't purify the carbon enough. They absorbed a bunch of neutrons, and they lost patience with the program, abandoned it, and probably were well ahead of the rest of the world developing nuclear weapons up until that point. But so the carbon has to be very pure, carbon-12. But the carbon will moderate the neutrons. But unlike the water, as the temperature increases here, what's going to happen? So you're not going to get the big drop in density that you do with liquid. And so these kinds of reactors, depending upon other details of how they're built, graphite moderated reactors frequently have, at least over some regimes of their operation, have positive void and positive temperature coefficients. Which makes them problematic from a safety standpoint. But aside from that, it goes through the rest of the system. Gas, it's usually either helium or carbon dioxide. Helium, because helium has essentially zero cross-section for absorption, but carbon dioxide is more effective in the turbines, so carbon dioxide with carbon-12 is also often used. Graphite is moderator. Again, you don't need a pressure vessel. I think we covered all of that. So then we can get to breeder reactors and liquid metal cooled reactors. So you probably in heat transfer talked about the very impressive thermal conductivities and heat capacities of liquid metals and salts. And so you can use molten salts or liquid metals as coolants. If you're trying to make a fast reactor, you don't want anything that has a low molecular weight in it, because things with low atomic weights slow the neutrons down, and you don't want to slow the neutrons down. And so the reason that they use liquid metals, typically sodium, is because a neutron can pass through sodium and hardly change its speed. It doesn't slow down appreciably as it bounces off the sodium nuclei, unlike the others. So you use liquid sodium, pump the liquid sodium through this system, and then typically have another liquid sodium loop, and then finally you have a steam loop. So this looks like a pretty complicated system. So it might surprise you that the first liquid sodium breeder reactor that was built was put on a submarine. The second submarine, nuclear-powered submarine that was built, Seawolf submarine, was a breeder reactor with liquid sodium. So who besides the military, so you all know how sodium reacts to water, right? And reacts almost as violently in air. That is, metallic sodium will oxidize to sodium oxide just in air. You need moisture to do it. So, who besides the military would put a whole bunch of liquid sodium in a submarine underwater, right? So they designed this very carefully, and they were building this at the same time they were building the one for the Nautilus reactor, the first nuclear power. And those two submarines were launched at the same time. And technically, the liquid sodium cooled reactor worked well. There was actually less corrosion and less problems like that with it than there was with the other one. But the consequences of, so whenever you have something like this, there's always going to be some sodium leak somewhere, and when that's inside of a closed vessel like a submarine underwater, they just said this is just too much of a risk. And so they actually decommissioned that reactor and replaced it with a conventional pressurized water reactor. That's the only time that I know of that it's been in a submarine. So So they're fast neutron-based reactors, there's no moderator. Sodium or sometimes a blend of potassium and sodium are used as a coolant. Because you don't have to pressurize the reactor vessel now because you're generating steam, so the steam still has to be pressurized, but the reactor vessel doesn't have to be. Sodium can become radioactive, and sodium and potassium react violently with water and the unit air. The second sodium heat exchanger isolates the sodium-potassium coolant in the core from the steam turbine, and that is, so let's see, why do you have two heat exchangers here instead of one? And the idea is that this heat exchanger is problematic because you have sodium on one side and water on the other side, so there's a pretty good chance you're going to have a problem there. It's going to be a major problem. And if you were to put that heat exchanger here, that major problem will become infinitely more complicated by the fact that the sodium is radioactive. So here you're dealing with non-radioactive sodium, at least, but it's a sodium water reactor. So to prevent this problem from becoming almost impossible when it eventually happens, they put two heat exchangers. See, new fuel is consumed, the fuel ratio raises at the time from 0.6 to 0.8 in a typical reactor over 1. It's designed as a breeder reactor. So, then we get to the light water graphite moderated reactor. So light water cooler graphite moderated reactor. This is a design of the RBMK reactor, which is a Soviet design, and has actually a lot of technical advantages. This is a Chernobyl reactor, but there were a lot of things about it that were actually quite advantageous, but a couple of them were spectacularly bad. So here it's just water cooled again, and now you have just graphite moderation. So because it's water cooled, the reactor vessel, the tubes here still have to be pressurized, but the reactor vessel doesn't. And part of what that means is that because it's not pressurized, if you can, and they did, you can actually do maintenance on this in terms of replacing, if you build this the right way so that the fuel rod doesn't necessarily, it's shown here inside of what would be a pressure vessel, but it doesn't actually have to be inside of it doesn't have to be pressurized, so you can put fuel rods in and out. So one of the advantages of this reactor, you can actually do maintenance on it without shutting the reactor down. You can swap two fuel rods around while it's operating because you can pull the fuel rods out. You don't have to depressurize the reactor to do it. So that's one. Has a lot of other advantages as well. The Soviet design standards didn't call for a containment vessel, so that's a requirement in the Western world. It's now a requirement worldwide, I think, is we've got a containment vessel around the core. And the Chernobyl reactor did not have a containment vessel. And there were some details of the design here. We'll go through the accidents and talk about that a little bit more. So, the Soviet, it's called the RBMK reactor. Fuel is in the pressurized fuel channel in the graphite block. Steam passes directly to the turbine. Fuel can be exchanged without reactor shutdown. So how long does it take those to decay back to things? And if you could extract the plutonium, how much difference does that make in terms of what you have to do to treat the fuel? So we will talk more about that, but so those are, this time it's mostly math, differential equation kind of basis of the problem. Any questions about any of that? You see how to feel like you can attack that?
So I'm just curious if you do this first. We have a lot of info sessions every day.
We do.
Can we extend this homework?
So we can. I want you to take full advantage of this career fair. So I think the career fair starts at 9 o'clock. Is that right, on Thursday? So I will propose that we can extend this homework due date till, so if we extend it to Friday evening, time to eat. So we'll make it due Friday night, and I will try to end class around 9 o'clock. Next Thursday, and participate.
Is it going to be a review and that's not detailed?
So we will put the test off. So I want to talk about the accidents, and so one of the things that you really need to, at least I you to know is, I want you to know the details of what caused these accidents and what might cause a new accident. Be well informed in terms of the risks of nuclear power, and there's a bunch of policies in, so that will take at least until 9 days. So we'll have a review probably on Tuesday, maybe again next Thursday. So, all right. In this case, it's just actually not like eight, but, so, you should be able to just look at that. That's really good news.
Yeah, the natural architect.
There are lots of them. Yeah, there are a lot of them. There is a lot of them.
Right? So that should be, I will correct that right now, I'll send an email out. So what we really want to talk is if we fought at the law, sorry, this is mentioned here.
Yeah.
So if you take the log, then the log, then
Yeah, I don't understand why you're not like that.
Yeah.
what we really want to talk is log and then
Okay. Okay.
That's thought, no mind.
Cool.
Thanks.
Thanks, everybody.